Hello everyone, I welcome you to another video lesson on Markov Chains. In this video lesson, we'll look at how to solve a few problems on Markov Chains using the R programming software RStudio. To help us solve these problems, we'll look at five functions. The first one will be to define the TPM, the transition probability matrix of a Markov chain. Second function will help us how to multiply two matrices. Third one will be to define a Markov chain. Fourth one will be to find out whether a given Markov chain is ergodic by nature. The last one will be to determine the steady state probabilities of the Markov chain. The problems that we'll discuss are the same set of problems that I discussed in my previous video on Markov chains, where I solved them analytically. I've considered the same set of problems and I've solved them using RStudio. So if you have not watched the video on the analytical solution of the problems on Markov chain using Chapman-Kolmogorov equations and steady-state probabilities, you can visit the link given in the description. It will lead you to this video, the video number 2 on Markov chains, the corresponding playlist. You watch them and you can come back here. Moving on, we'll look at the first function as to defining a matrix. We'll define a matrix by listing down all entries of the matrix, and then we'll give the important specification that the entries are to be read row wise. This is given by the command by row is equal to true because RStudio usually understands matrices column wise. So to be very clear about that, we give the command by row is equal to 2 and we also specify the number of rows. For example, a 2 by 2 identity matrix can be defined as matrix of C1001. We give the command by row is equal to true, and then we also specify the number of rows as 2. The second function we look at is to multiply two matrices where the orders are compatible for matrix multiplication. We assign the product of the two matrices to the variable C, and that will be enough. The next is to define or declare a Markov chain. We give the name of the Markov chain as chain underscore name, and the command goes as new of Markov chain within quotes, and we list all the states in the state space of the given Markov chain, and then we also define the transition matrix as we call it as chain matrix, and we assign it to the transition matrix part. So it is essential that before this command is defined, we define what we have already declared the TPM of the corresponding Markov chain. For example, I have declared a Markov chain called as luck chain, in which there are two states win and lose, and whose transition probability matrix is given by the matrix luck matrix, which must have been defined before this declaration. The fourth piece of code that we look is to find out whether a given Markov chain is ergodic by nature. So this goes by the name is.ergodic function. We'll go for the chain name there. The chain name can be by your choice. I've given an example for a chain whose name is luck chain, and we'll find out if this chain is irreducible. And at the same time, we'll also find out if the periods of all the states of this Markov chain is 1. So if both of these are met, both these conditions are met, when there is a double ampersand symbol, we know that it's an AND condition. Both these conditions are met. We declare the chain as Markov chain. Otherwise, we declare the chain as being ergodic. Otherwise, we declare that it is not ergodic. The fifth function is to find the steady state probabilities. So we'll define a Markov chain before calling this function, and we call the function called the steady states. This S in the states is in uppercase, and we'll pass the name of the Markov chain as an argument, and we'll print the outcome of this function, which will be the steady state probabilities of the corresponding Markov chain. Now, with that introduction, we'll go into the list of problems that we have solved analytically, and we'll solve each one of them using RStudio. The first one is the student problem. The student has a study habit in which he studies or not, or chooses not to study, and the probability with which he studies and he does not study are given in the problem. If he studies one night, he's 70% sure not to study the next night. On the other hand, if he does not study one night, he's 60% sure not to study the next night as well. So defining the TPM is not a big task. So we've defined the TPM. It has two rows and two columns. We've discussed this in the other video. So once the TPM is ready, we can write down the code for the TPM. So our TPM will be a 2 by 2 matrix. The entries of the TPM are listed: zero point 0.3, zero point 0.7, zero point 0.4, and zero point 0.6. And we specify that the matrix is to be read row wise. And we also list the number of rows in the TPM. This is followed by the declaration of the Markov chain. I call the Markov chain a study chain and the corresponding matrix a study matrix. I list the states of this Markov chain as studies and does not study. And I assign the transition matrix as a study matrix, which I've defined just a little while ago. And then we examine the ergodic nature because we need to calculate the steady state probabilities of this Markov chain. So we include the irreducible nature and the periods of every state in the Markov chain. And this is what we get. As a result, we find out that this Markov chain is in fact ergodic as part of the code. And once we have determined that the Markov chain is ergodic, we calculate the steady state probabilities and print them. So now let's look at what happens when we run this code using RStudio. All right. So we have the question before us. Now, before we start writing the code and execute the code, we'll first ensure that the package Markov chain is installed in the RStudio that we are using. We have checked it. We have typed the name of the Markov chain package, and we have seen that the checkbox is active, so the package is installed. So we can, in fact, execute all programs that we need using this package. All right. So we have the question up there. I've made it as a command. There is this code on the transition matrix. There is the declaration of the Markov chain. There is the examining of the ergodic nature of the Markov chain, and there is the calculation of the steady state probabilities. Now, all part of the code is, present here. We'll just run. We'll execute the chunk, and we'll have a look at the answer. Executing the chunk here, we get the answer below. Markov chain turns out to be ergodic. The steady state probabilities are 0.3636 for the student to study in the long run and 0.6363 for the student to not study in the long run. We got the same answers the other day as well. We got them as fractions 4 by 11 and 7 by 11 that can be verified. We'll go to the next problem now. The next problem is on the gambler's luck. A gambler's luck follows a pattern as given below. If he wins a game, the probability of him winning the next game is zero point 0.6. If he loses the next game, zero point 0.7. So the corresponding TPM is obtained as a 2 by 2 matrix with 4 entries. And we are to find out three probabilities: the chance that he wins the second game, the third game, and in the long run. We'll execute this code by first defining the transition matrix, the 2 by 2 matrix, if we did like in the previous question. And we'll declare the Markov chain. I'll call the Markov chain as the luck chain, the corresponding matrix as luck matrix. And then we'll also define the initial state probabilities, a one row, two column matrix whose entries are 0.5 and 0.5. That's because the question states that there is an even chance that he wins the first game. So the first game is an equal probability that he will either win or lose. So the initial matrix has entries 0.5 and 0.5. Following this, we multiply the initial matrix with the TPM and we get the answer. We store it in the P1 matrix and we ask that the first row, first column of the P1 matrix is printed. That's the probability for winning the game and we'll get the output. Similarly, we multiply the TPM with itself, get its square, and we also multiply the initial probability with the square of the TPM and we try and print the first row, first column of the product matrix that will return the answer, the required answer of winning game 3. And then we also check whether this Markov chain is ergodic. We write the code for that. And following that, we print the steady state probabilities. Having done all this, let's find how this execution is done. I've typed the question as a command. I've declared the TPM. I've declared the Markov chain. I've defined the initial state probability matrix. I've defined the answer for question one, the answer for question two, and I've checked the ergodic nature, and I've also calculated the steady state probabilities. Now let's try and execute this chunk and find out how this pans out. Running this chunk gives us this result. The chance that he wins game 2 is 0.45. The chance that he wins game 3 is 0.435. The code finds out that the Markov chain is ergodic, and the steady state probabilities for winning are 0.4285 and for losing is 5714. That completes this part of the code. The next problem we'll look at is the tourist plan consisting of three cities A, B, and C. Description, we in fact define the TPM as a 3 by 3 matrix with 9 entries. So moving on to the code, we first define the entries of the matrix. We list the elements row wise, and then we declare the Markov chain. I call this Markov chain as the 2 chain and the corresponding matrix as a 2 matrix. And then we move on to examining the ergodic nature of the matrix of the Markov chain. And having confirmed that the Markov chain is ergodic in nature, we print the probabilities of the steady state. Having discussed the code, let's find out what the execution does in the RStudio. So given the question as a command mode, the tools plan is discussed there. The TPM is defined, the Markov chain is declared, the ergodic nature is examined, and the steady state probabilities are printed. Now let's execute this chunk and wait patiently for the answers. The output is here, and we see that RStudio confirms that this Markov chain is ergodic, and the steady state probabilities are 0.40, 0.45, and 0.14. We can recall we found these answers to be 8 by 20, 9 by 20, and 3 by 20, which are the fractional representations of these three decimals. So this program is done. We'll go to the next problem. Next problem was on the weather of a given day. When March 1 is known to be a dry day, we try and find the chance that the weather is rainy or dry on March 3 and March 5, and also find the probability that in the long run, the given day could be. Having defined the TPM, we'll list the elements of the TPM row wise. And we'll declare the Markov chain. I call this Markov chain as the weather chain and the corresponding matrix as the weather matrix. And I define the initial probability matrix as 0, 1 because we know that March 1 was a dry day. So P naught is a 1 by 2 matrix with entries 0 and 1. Then we calculate the square of the matrix because we want the weather on the 3rd of March, which is 2 days away from March 1. And the fourth part of the matrix because we want the weather on March 5, which is 4 days away from March 1. Having calculated these two powers, we multiply these by the initial probability matrix to get the answer for the probability of March 3 being a dry day and March 5 being a dry day. And then we'll examine the ergodic nature of the Markov chain. And having confirmed that the Markov chain is ergodic, we'll execute the code to find the steady state probabilities of any given day being rainy or dry in the long run. Now, having discussed the code, let's find out how the code pans out in RStudio. I've defined the TPM here. I've declared the Markov chain. I've defined the initial probability matrix. I've found the square and the fourth part of the TPM. I've examined the ergodic nature. I've calculated the steady state probabilities. We'll just execute this chunk and wait patiently for the output. We have the answers here. March 3 will be dry with a chance of 0.416. We found the same answer as a fraction being 5 by 12. March 5 could be a dry day with a probability of 0.400. We found this as a fraction. There is 173 by 432. And the code finds that the Markov chain is ergodic. And the steady state probabilities are a 60% chance of being dry and a 40% chance of 60% chance of being a rainy day and a 40% chance of being a dry day. We'll move on to the last problem now, which was again on a gambler who starts a bet with 3 rupees in his purse. He wins 2 rupees and loses 1 rupee with the probability of 1 by 4 and 3 by 4. And he stops playing if he's either lost his entire amount or if he has won at least 3 rupees. We discussed how to define the TPM of this corresponding Markov chain. I've listed them down here. So moving on to the code, this is how we'll define this 8 by 8 matrix. We'll list all elements row wise and specify the number of rows as 8. And we'll declare the Markov chain. I call this Markov chain as the G chain, as being the gambling chain, and the matrix as the G matrix. Now, since we want the game to continue for at least 4 rounds, we'll have to find the third part of the TPM. So I'll define first the initial probability matrix, a 1 by 8 matrix with 8 entries, and the fourth entry is 1 because he has 3 rupees to start with. So that is the fourth entry. The first 3 entries are for 0, 1, and 2 rupees respectively. The last 4 entries are for rupees 4, 5, 6, and 7. Having defined the initial matrix and the TPM, we can get the product by first finding the third part of the matrix, and I'll multiply these two, and I'll in particular add the entries which are in the second, third, fourth, fifth, and sixth positions of the resulting 1 by 8 matrix, because I want to leave out the possibility where the first entry denoting the 0 rupees and the last two entries which denote the 6 rupee and the 7 rupees are not considered. So when I add all these probabilities, I'll get the required answer. So that completes the code part of it. Let's find out how the execution runs. So I've written the code for the TPM, the 8 by 8 matrix. I've declared the Markov chain as G chain, and I've defined the initial probability matrix as well. I found the third part of the matrix because we are interested in the result after the third bet, and then we have multiplied the two, and I've tried to return the answer for the question that was asked. Now we'll run the code. We'll patiently wait for the final answer. Yes, we get the probability of the gambler continuing to bet for at least 4 bets is 0.421875. We got the same answer as the fraction 27 by 64. This answer is the decimal form of it. So that completes all 5 problems that we discussed yesterday. We discussed them and we solved them analytically in the other video, the second video on Markov chain. Today, we have looked at how to execute all these programs using the R studio. I hope you enjoyed this video lesson. I'll quickly follow this up with another video. Thanks.